Thank you so much, Changwon, for the intro. And yeah, great to see former interns from NASA going off to do amazing things. So I'm looking really forward to seeing all the great work and coming out of your lab. So the talk that I put together today is probably a little different than your conventional, I think, AI or robotics talk. I really wanted to talk about a journey that we've been on for the last decade or so, specific to starting with the Mars rovers, but really dealing with robotic exploration and how we're starting to think about how we can increase autonomy, and make these robots more capable for performing their missions, and what are some of the challenges in how these robots are operating today, and the challenges in being able to incorporate this type of technology kind of specific to um, the unique elements of planetary robotics. So, uh, okay, here we go. All right. So as you all know, being in this space, robotics has gone through a lot of advancement over certainly the last decade, if not longer. And most of that work, I would say, is focused on really replacing what humans can already do with robotics and artificial intelligence. Um, and I think this has very direct applications in terms of being able to industrialize basic operations, be able to improve warehouses, be able to do assembly lines more efficient. Like this is kind of the natural expectation for what you would apply robotics to. And you have the benefit of a lot of data. You have performances that you can measure with the human performers. You have tons of observational data that you could train models with. And in many ways, while this is not a hard, or this is not an easy problem, at all, this is a very hard problem. Robotics broadly is very hard. But in many ways, it makes this a lot easier given that there's a ton of data to support developing these types of models. And furthermore, there's a ton of data that you can validate these models on in terms of being able to deploy them in actual environments that you can do safely and do testing. What I think we've seen much less advancement in is in the domain where humans cannot perform these tasks. So, if you recall, like the Fukushima nuclear meltdown, where they needed to do maintenance on the reactor, humans obviously couldn't go in there and do it. And it was very challenging, not just to build robotics that can, work underwater and operate in those environments, but just doing simple manipulation and navigation in these not just unstructured environments, but disaster site environments was really difficult. And I would say that we haven't really made a whole lot of advancement there. Same thing with like Deepwater Horizon, which was the oil well that blew out and caused a massive oil spill deep underwater. All of these robotics were typically teleoperated. It was very difficult to be able to manipulate these valves underwater. That would be very easy if you can just send a human down there, but you can't. Um, and we have the same problem with space robotics. So as we obviously have multiple rovers on Mars. We're starting to develop rovers for the Moon program as Artemis and kind of the human space flight program ramps up for the Moon. And in many cases, where we're going to has never been visited. So we need to design and build robot autonomy here on Earth that works in a completely unseen environment where we can't just go and test it. We don't have data to support developing, and we have a very low tolerance for failure. So the expectation is that it has to work, and it has to work essentially perfectly in an environment that we've never seen before. Um, so that I think makes space robotics pretty unique among the world of research robotics, where a lot of the methodology, when we talk about generalization, are very hard to validate whether or not those methods actually work in these environments that are just unseen. Um, so, that's the challenge, and there's good reason why there's just been very slow progress in this domain. Um, so as we think about planetary exploration, in the early days of space exploration, all of the science instruments that we put in space have typically been orbiter missions or flyby missions. So they're just spacecraft. They stay in space. We understand orbital mechanics very well. There's not a heavy need for autonomy in these spacecraft. So you think about, Voyager, Galileo, Cassini, all of these big flagship science missions that were, designed to kind of explore the solar system, did not require a huge amount of autonomy. And so that makes sense in terms of managing risk, to be able to build a science instrument that you can reliably send out to these, very far places and reliably collect data. And so we've done that, and we've had kind of flyby missions across nearly every object of interest in the solar system. We've had multiple orbiters, but now as we can only learn so much from orbit, as we want to get into the atmosphere, onto the surface, and potentially into the subsurface, in terms of drilling uh, into the surface or navigating subterranean cavities and lava tubes, these types of things. Um, and going beyond that, returning samples back to Earth, which is of particular interest for many of these planetary bodies. These all require substantial autonomy because you can no longer pre-plan, things like orbital pathways months in advance. These vehicles need to be reactive. They need to make decisions on their own. They need to operate reliably and essentially near perfectly without human intervention. And in many cases, like we just don't have the technology to do that yet. So that's kind of one of the reasons why in this chart, as you go down, kind of below this kind of orbiter layer is the domain of robotic missions. And as you go to the right, where you're looking at more distant objects and objects that are more expensive or take a lot of time to get to, um, the amount of cost in doing this, and the amount of technology required to do this just becomes massive. And so we've just never been to these places. Like on the bottom right of this chart, there are no planned missions um, currently, just because we don't have the technology to do them yet. Um, so I'm going to talk a lot about Mars today specifically, and surface missions specifically. But I want to keep this big picture in mind in terms of our goal is to build robotic capabilities that ultimately is kind of universal to this chart. We want to go kind of to every place, um, down to a level of complete autonomy. So how we think about managing risks for such a mission classically, and so here we're calling it robotic space exploration 2.0, which is the current way that we're thinking about designing these missions, is if we want to go to Mars, we start off with an orbital reconnaissance mission. So we send an orbiter around Mars, we map the planet, we try and understand, surface geology, surface geometry, weather patterns, all of these things from a safe distance. And so going there, we don't know anything about the surface. So the uncertainty around the terrain and the environment that we actually want to go to is very high. But the complexity of that mission is actually very low. The risk of that mission is very low because you're not actually going into that environment. You're just orbiting the planet. So after you gain that information, you then design a follow-up mission that's a lander. So this is like Viking, for example, that we landed in the 70s, where it's just a static lander. So we can pick a site based on the orbital data, get on the surface. So there's medium uncertainty around the environment. But landing on the surface of Mars is like, it's famously difficult. So just accomplishing getting a vehicle on the surface intact requires, a lot of engineering and a lot of effort. So, this is kind of medium uncertainty, medium complexity. So once we're on the surface, then we can really start to understand kind of what the terrain properties are, understand kind of what it would take to actually drive on the surface. And so the next mission after this is then designing a surface mission where you have a rover, where you understand the terrain enough that you understand the obstacles, you understand the rock density, you understand kind of the basic um, terramechanical properties of the regolith. So the uncertainty of the terrain is now low because you've de-risked it, but the complexity of the mission is now very high because you have this very complex rover system, robotic system, that you now need to operate on the surface. So the challenge is that this requires 3 missions to be flown, And the level of investment to do this, this has taken us 30, 40 years to go through this process where we're now comfortable driving on Mars. Um, and if we want to do this anywhere else, the knowledge gained here is very specific to the environment. So, for example, NASA is very interested in going um, to ocean worlds, is what we call it. So any icy body or a body that has liquid water. So this is typically like the Jovian moon. So like Europa, Ganymede, the the moons of Saturn, like Enceladus. All of these bodies have liquid water that are very important to understanding kind of the origins of life and the origins of the solar system. But the cost and the time it takes to get to these places just amplifies the cost of this overall cycle. So if this takes 40 years to get on Mars, it might take 100 years to be able to repeat this cycle on a place like Enceladus. So the challenge is that that's not scalable. As we want to go further and as we want to be more ambitious about our robotic autonomy, we need to understand and deal with risk in a different way. So as we start to think about this for future missions and what we're calling here robotic space exploration 3.0 is how do we do this in one shot? How do we fly? How do we design a mission so that we can land in a place that we've never been? We know very little about the surface of that place, um, where the uncertainty is extremely high, the complexity. Uh, we want to stay relatively low where we can reliably land and assess the situation. Um, and then from that, be able to map the surface and deploy a robust robotic platform that has a lot of not just physical adaptability in terms of being able to have locomotion modalities that can span a whole variety of surfaces and a whole variety of different mobility gates. So the illustrations here is actually for a mission concept that we've been developing called EELS, which is a snake robot designed for Enceladus. Um, and this robot then is in principle capable of being able to navigate in a very kind of safe and robust way around the surface to be able to then start to map all of the terrain properties, start to understand kind of how to locomote in that environment safely. Um, and then furthermore, like once you have that information, be able to actually achieve some kind of mobility mission of going down into, in the case of Enceladus, you have all of these like cryovolcanoes where liquid water is jetting out of these fissures, and we don't entirely understand the process. We know they exist because Voyager has seen them, Cassini has seen them. We've observed this phenomenon where these jet water plumes are being ejected off of Enceladus. Um, so we want to go to those locations and fall into into those fissures and find the water. But we have no idea what those fissures look like. We can run kind of as much physical simulation of ice formation and these jet phenomena as we want, but there's just so much uncertainty around the actual processes involved that the only way to really have confidence of being able to navigate that environment is to go there and start collecting data. So this is the challenge, is how can we think about being able to design not just the robotic platform, but also the software and autonomy such that we can achieve all of these things in one go in a way that we are comfortable that we're still managing risk appropriately. Just given the cost of these missions, you can't have a probability of failure that's anything lower than high 90 or a probability of failure that's within a couple of percent. So success needs to be in the high 90s for the mission. Um, so so that's kind of the challenge. And so what I wanted to talk about here is kind of how we're thinking about that, um, and really where we started. So I want us to kind of go through some of the background on rover navigation and autonomy specific to Mars, and just how are we navigating on Mars today with our current rovers, and what is the state of art for autonomy? And I would say this is classical autonomy. So there's not a lot of learning based. technology that has gone into the current flight systems. Um, well, we've been investing a lot into understanding kind of how learning-based systems can augment our current autonomy stack. So I wanted to talk a little bit about some of that work and some of the results from that. Um, in a similar vein, we've also had a bit of investment in understanding kind of how AI and machine learning impacts science gain. So all of these missions are really driven by a science goal. Like we almost never go to a place purely for the reason that it's difficult or it's an engineering challenge. There's always a science driver around answering a key physical question that is just unknown to the science community. So we send a mission out there with instrumentation to be able to answer a very specific question. Like, unfortunately, no mission in NASA is like curiosity driven. We never go to a place just because we haven't been there if there isn't a very well-defined science question that we need to answer, and going there is the only way to answer it. Um, so we spent a little bit of time kind of trying to figure out how machine learning can actually improve science gain, given some of the challenges with, again, specifically with Mars that we have in really interpreting science data. Um, and lastly, I want to talk a little bit about model adaptation, and kind of the balance between how we think about model generalization versus model adaptation, and where the applications are between those two. Um, and really dealing with kind of what I wanted to start off with in terms of just ground traversability and navigation, as well as the stereo system. And I'll talk a bit about what that looks like on the current Mars rover. Okay, so I think this part's obvious, but why is driving on planets other than Earth difficult? So obviously there's no GPS, there's no roads, there's no power. Um, you have an unstructured environment. But you also have typically limited sensors. So if you look at Waymo's, Waymo's is like an autonomous vehicle company that's a subsidiary of Google. They are everywhere in Los Angeles. I don't know if you guys have them in Korea or similar vehicles, but I feel that like every 10th car on the streets of Los Angeles doesn't have a driver today, which is impressive. I think that they've done a lot of really great work in really understanding how to deploy a safe autonomous system in a complex environment, such as the city streets of Los Angeles and San Francisco, and I think they have them in Austin and maybe one other city. Um, but the advantage that they have is that they have a very wide collection of sensors. So they have radars, they have LiDAR in every corner of the vehicle. They have all sorts of ultrasonic sensors, stereo cameras. There's just an incredible array of sensors on these vehicles, such that every square inch around the vehicle in 360 degrees is well mapped, um, using very reliable sensors. So that the power budget for that is just immense. So like we can't even fly a single LiDAR on Mars today because it consumes too much power. And so there's just a lot of limitations in terms of just the sensing capabilities that you can typically have on these missions. And and lastly, and this is kind of unique to a lot of the planetary bodies that have less gravity than Earth, and something that we don't think about too much, I think, in terms of developing robots on Earth. So the regolith on Mars, and even more so on the Moon, um, due to its kind of fine structure and low gravity, has this phenomenon called opposition effect. And I'll show you some of the data of what this looks like in a later section in this deck. But just to quickly kind of give it a taste for the challenges, it results in really kind of poor photometric properties that create all sorts of problems for vision-based systems. So when we talk about robot autonomy and visual perception, there are certain lighting conditions that occur on Mars and the Moon that just make it very difficult to be able to accurately perceive the geometry of the terrain that really is not so prominent on Earth. That just makes kind of additional challenges driving on these surfaces. Um, and lastly, if you break your vehicle, there's no one there to fix it. And so the system has to work very, very reliably. If anything has a critical failure point, then those things need to be really tested, and you have a high confidence that there's no single point of failure. Oh, and lastly, and this is really, I think, one of the biggest challenges, most robotic platforms like outside of Earth need to have a radiation hardened platform. And radiation is particularly hard on computing systems. So the CPU, for example, on our current Mars rover, Perseverance, is still a Rad 750, which was designed in the late 90s. It's a PowerPC core. It runs at a woefully slow 133 megahertz. And it's essentially the same core that goes into a 1998 iMac, if anyone in the audience is old enough to have had that computer. So, I mean, it's really ancient by computing standards, but this at the time was the best radiation hardened computing platform available. And this is changing pretty quickly. I think there's been a lot of development in radiation hardened computing just recently, given that there's a lot more kind of interest in development in space. But there's nothing that is remotely close to kind of the high performance computing that we find in just kind of modern GPUs and workstations today. So everything we develop need to operate on computing that is literally 30 years old, at least on the current Mars rovers. Okay, so I want to give some background in terms of kind of some of the methodologies involved in how uh, Perseverance specifically, but this actually applies to most of our Mars rovers, how they navigate. Um, so conventional to, a lot of, a lot of robot path-based planners work. So this is a tree-based planner. So it plans out to a horizon of 6 meters, and it estimates um, all of these candidate trees based on wheel steering geometry that are viable for the physical platform. Um, so the challenge with autonomous driving is that among all of these possible paths that the vehicle can take, we want to pick the best path, and best needs to be defined in some way that guarantees that it's a collision-free path between the vehicle and the terrain. So we have a global planner, which is typically planned for hundreds of meters out, and typically those are determined from satellite imagery. So we have some goal that's way far away that typically is a science site. So there's something that we want to sample that's far away, and we say go there. And so that's typically in a 1 meter resolution map. So the local planner is centered around the robot, and it goes out 6 meters. And so it needs to pick the best path among several thousand candidate paths that's consistent with the global planner. So every time the vehicle moves a couple meters, it replans the local planner. And the objective function in terms of what path it takes is determined by A, its alignment with the global planner, and B, whether or not it's safe. So how we determine safety is with an algorithm we call ACE. It stands for Approximate Clearance Estimation. I'll talk a bit about what it does, but it essentially guarantees the safety of the rover based on the geometry of the rover itself and the terrain. And so ACE is run at every 25 centimeters along this path. And if every point along that 25 centimeter chain of a given path evaluates as safe, then the whole path is considered safe. Okay, so what does ACE do? So safety is geometrically defined here. So we have to solve this problem called kinematic settling. And so that basically given the location of the rover, XY position, and the yaw of the rover, just being its orientation, and an elevation map. So this is like a 2.5D map of the height of the surface at every given XY point. So given those four things, we want to estimate the Z, which is the position of the rover's kind of center datum in height, based on kind of how the wheels position against the terrain, and then the roll and pitch of the body of the rover. And in order to get those things, you also get the suspension angles of the suspension geometry. Once you have all that, then you can basically estimate whether or not the body of the rover actually collides with the terrain, and then you get this binary collision, no collision. So that's the collision checking part of it. The rovers, so all of the rovers that we've ever sent to Mars, so this is Sojourner, which is the very first tech demo, the Mars exploration rovers, so Opportunity and Spirit, Curiosity, which is the Mars Science Laboratory, and the current rover, Perseverance. All of those rovers have the same suspension geometry, which is this rocker bogie system. I won't go too much in the details of like why it's this way, and I won't go through this formulation. So basically, I just wanted to highlight just kind of how it works and what geometry we're trying to solve here. So in the system, we have the rocker, which is the main linkage that connects the front wheel to the back, what's called the bogie. And so the bogie connects the back two wheels, and it's just free castering, it's just idling. So the reason why you have this rocker bogie system is that it tends to significantly reduce the amount of body roll based on the terrain geometry over a rigid suspension system that we would find like on a four-wheel vehicle. So it typically gets about half. So if you were to climb up on like a large rock or a large piece of relief with a four-wheel vehicle versus a rocker bogie system, typically your bank angle of the body will be about half of what you would find on a four-wheel vehicle. So if you just run the geometry of all of the angles involved, you get kind of these equations that just define given the suspension geometry, where are the wheel locations in space? So this is just solving a kinematic problem. Okay, so what ACE does is it doesn't actually compute kinematic settling. So the problem is that there is no closed form solution to be able to solve for the distances here. The D1, D2, D3, you cannot solve them in closed form to get well, given the joint angles, you cannot get the distances, or you cannot optimize like what those distances are to be able to solve for ground contact. So it's a nonlinear optimization problem. So what ACE does is basically determine the worst case bounds of what the body geometry is based on the terrain and kinematic settling. So how ACE works is we took all the data from MSL, this is Curiosity, and looked at all of its roll, pitch, yaw throughout the entire mission and determined the volume that the wheel would appear in, and created a envelope of basically a 99% box that the wheel, these are the bounds that the wheel ever kind of occurs in given the suspension for all six wheels. So next is given the terrain, we create a bounding box essentially that is the intersection of the extent of that terrain within the wheel box. And we do that for all six wheels. So next, we essentially compute the most extreme angles of the suspension geometry such that one of the wheels is at the maximum and minimum of each of those bounding boxes. So this is just, there's only 2 to the 6 combinations of all of the different geometries. So you can just easily enumerate all of these suspension geometries. And based on that, you can then get the worst case for what the body pitch and roll is. And given the body pitch and roll and Z location, you could then compute collision. So this is very simple to evaluate. And it essentially guarantees you a collision-free kinematic solution. But it's an approximation. So this runs in about 10 milliseconds on the RAD 750, which is great. The problem is that that's still infeasible because while you can evaluate a single path, there's only a dozen or so evaluations along to validate a single path. There are thousands of paths. So it would be computationally infeasible to be able to estimate every path to be able to plan using even this upper bound estimator. So instead, we have to make this a two-stage algorithm. There has to be a heuristic that first determines a very inexpensive evaluation of path cost. And so in kind of classical robotics, when you have path planners, you have a cost map, and you just plan to minimize the aggregation of cost across the path that you compute. So this needs to be very cheap to evaluate. So for us, we basically have um, a couple very simple measures of path length, slope, terrain roughness. I believe there's like a step hazard of like basically maximum gradient of the surface. So these are all things that you can kind of estimate very, very simply. Uh, and given this estimation, you can order the paths such that they're ordered in like lowest cost to highest cost. You're basically prioritizing which paths are most likely to be good paths using this simple heuristic. So we can do that thousands of times for every path um, to create a priority list. And then given some top n of uh, the best candidate paths, we run ACE across all of those paths to then um, determine whether or not that path is collision free. And we basically take the best in terms of the prioritization, the best path that's collision free. So once we find a collision free solution, then we typically accept that path. So this was heavily V&V'd using, so V&V is it stands for validation and verification. So it's the process for testing these capabilities that's such that we have confidence that they're going to operate as we expect in the environment that we expect to deploy them in. So this typically starts with a lot of simulation in Monte Carlo. So Perseverance landed in a location of Mars called Jezero Crater. That's this elevation map on the left is Jezero. So we took the actual the digital elevation map that comes from the orbiters that have mapped this location to create kind of synthetic surface terrains that we then run Monte Carlo heavily across to plan just kind of random paths through the synthetic terrain to validate whether or not there's kind of any failures that are unexpected in this system. And the system is called ENAV. It stands for Enhanced Navigation. And furthermore, beyond simulation, then we do actual testing. So we have a vehicle that we call Scarecrow. That's the vehicle here on the top and bottom. The main purpose of Scarecrow is that it has the exact same wheel geometry, the rocker bogie system, and wheels as the actual Mars rover. But the weight of this whole system is about a third of the weight of the actual rover. And so that's basically to offset the gravity difference between Earth and Mars. So the interaction forces of Scarecrow essentially match the interaction forces of the real rover that weighs 3 times as much on Mars. So that way we can do this like large scale field testing without any kind of gravity offset mechanism, because otherwise you need to have kind of cables and gantries and mechanisms to be able to pull weight off of the rover. So it just simplifies testing. So all of this was like heavily tested and deployed on the rover. And I'll show you some numbers on kind of how well that works. So currently this pot's a little bit out of date, but Perseverance is driving a lot. And that was really one of its main mission parameters is it had to drive a much further distance than Curiosity did because it needs to sample uh, regolith samples from a huge variety of different locations. So it's a sample return mission, right? So like Perseverance is collecting those samples that will ultimately be returned by some other mission. So all of these little red waypoints are sample sites where it needs to drill a hole somewhere, collect regolith, put it in a sample tube, and then it has a cassette where it stores those samples for later retrieval. So currently, Perseverance has driven about 36 kilometers. Um, so that actually makes it, that exceeded, I think, the entire mission drive distance of Curiosity. Opportunity, which is one of the Mars exploration rovers, actually has driven further. I think Perseverance will surpass that soon. And I'll talk a little bit on how it was able to drive further. Um, and we have this location here for our Intrepid helicopter that unfortunately had crashed in this kind of featureless dune region. We'll talk a little bit about that later. Um, so here, recently, we actually achieved the longest drive, at least in a single sol. So sol is a 1 day on Mars. It's just shy of an Earth day. It's like 23 hours and 40 minutes or so. Um, but Perseverance drove 411 meters in one sol, which, while that doesn't sound like a lot on Earth, that is by far the furthest that any vehicle has driven on Mars in a single day. So this is the actual imagery from that drive, kind of interpolated between frames. Perseverance only images once every meter. I won't show the whole thing because it's pretty long, but pretty incredible that this is done autonomously. Um, so one of the things that like this level of autonomy has enabled is the ability to do these long drives. So Perseverance has operated pretty about 90% of its total driving is being done autonomously now, whereas for Curiosity, only about 5% of the driving was done autonomously. And this, I think, not just represents a shift in the technology being kind of reliable and robust enough to be able to do this, but also what our risk posture is in terms of enabling that autonomy. So Curiosity typically didn't need to drive more than about 50 meters on a given sol. So for the most part, it would conduct basically a sequence drive, what we call a blind drive, where the operators, they can obviously see where the rover is, and they'll just select waypoints for the rover to drive to and pre-plan a drive path. So it has certain mechanisms to be able to stop if it feels that there's an obstacle in its way, but it's not autonomously determining its path to drive. If there's an obstacle, it will just fault out and then communicate that back to then ask for the human operators to create another drive. So most of Curiosity was done that way. Um, Opportunity actually did do a fair amount of autonomous driving using a much simpler mechanism, ENAV. An Opportunity that actually currently has the driving distance record on Mars, but it had the benefit of landing in a very benign location where you can kind of largely safely just blind drive for very long distances, just hoping that you're not going to encounter an obstacle. So we would never do that again, I think, in terms of that being really risky. But I think it was way beyond its current mission. I mean, Opportunity lived for like a decade past when they thought it would, that they planned the mission for. So toward the end of the mission, they were just being very ambitious around driving very far distances, which again we would probably never do again because that's super risky. Um, so I think this shows the success of classical autonomy in terms of really enabling much higher capabilities in terms of being able to drive much further distances. Um, but it has its challenges, and one of those challenges are that we're currently validating these and designing these things around kind of first principles thinking in terms of the laws of physics are the same everywhere, so we can design around that, and we can try and test for every possible situation we would expect to arrive in. And we've only done that through, back to the beginning of this talk, through very kind of rigorous pre-planning through previous missions of being able to understand what all of those imaginable situations are. Then once we get there, we can then look at our local environment and do some parameter tuning and some adjustments based on whether or not that environment truly is kind of performing and whether or not the system is performing as expected in those environments. So, like, where do things go wrong? And so one of the challenges is that this is all geometric. So everything in that map is just elevation. And so you have to perceive that elevation in some way. So we have a stereo system just with the calibrated stereo cameras that we have on the mast of the rover that produces a disparity map that you can ultimately, compute depth, and project that depth into an ortho-projected map, that you get something like we see on the left. So the grid line is going to represent the depth. Every gray area is a region where it didn't find stereo disparity, so it just returned no result. That's just unknown space. So the rover cannot drive in unknown space. It can only drive where it can see depth or elevation. But it's all purely geometric. So if you infill, what you would actually see in this case, you have bedrock on the left where that's perfectly traversable, but you have all of the soft sand on the right that is actually very hazardous. But if you go to what this stereo system actually sees, it doesn't know the difference between the two. So if you happen to have a path that gets you toward your global goal that brings you through sand, it'll happily just drive there. And one of the problems is that we've gotten nearly, in fact, every single rover other than Perseverance has gotten nearly hopelessly stuck in sand that we didn't anticipate at least once. And we had to go through kind of heroics in operation to be able to recover those rovers out of the sand. And the challenge is like once your slip starts to reach 100%, that means that as the wheels turn, you don't have any productive locomotion forward. You start to just excavate yourself into the ground. So the problem with MER, so that this is opportunity, no, this is actually Spirit on the bottom right, was they're commanding these blind drives. And so there's no obstacle per se, so there's nothing to fault the system out. So it's just spinning the wheels and it's running for an entire day. Like we can only communicate with the rover typically once a day, sometimes twice. So they come in the next day after a full day of driving and they find the rover just completely buried in sand. Um, and in many ways, I mean, it took weeks to get Spirit recovered from this. They thought they lost it. So now, like, we're very concerned around hazardous terrain types and not just geometry. And how do we start thinking about that in terms of rover planning? So um, we spend a lot of time now kind of applying learning-based methods to understand terrain properties. And so this is like a classic terrain classification semantic segmentation problem. And we started off using kind of the classical methods. So all of these are using some form of fully convolutional network of various varieties. We've made many iterations of this. But basically, we've just annotated what the terrain type is and given enough data on the actual Mars environment, train a model, try and validate that model against similar data, and do a bunch of kind of testing here on Earth. So we call the system SPOC. It stands for Soil Property and Object Classification. So this has been a research project that's been going on for probably 10 years now that hasn't been deployed to the rovers yet, but it actually works quite well. We can typically classify terrain, well over 90% accurate. And at least in all our simulation, it provides, at least an informed, it's able to inform our drive path such that we can still, even if it's not perfect, improve our safety margins. And similarly, kind of going back to the helicopter, so one of the challenges with the helicopter is it flew over featureless terrain and it uses visual inertial navigation to be able to understand its attitude in space. And so basically it lost its feature tracks and then it went into a recovery mode where it tried to do an emergency landing in a region that had essentially it was a featureless region of just smooth sand. So ultimately that's what led to the crash. And so now, as we're thinking about future helicopter missions, we really want to know, like, not just properties around navigation, like what are safe sites to land in terms of like geometric safety, but we also want to understand kind of what the nature of the terrain is as far as system performance, such that we can estimate where those failures might occur and avoid those areas. And in this case, not fly over featureless terrain that would create failures in the navigation system. And you can easily classify featureless terrain with something simple like a terrain classifier. So how we collected data for this is a couple years ago, where we created this crowdsourced project called AI for Mars. And I don't think this is actually open now. We closed it off because we haven't continued developing this. But the idea was just to open this to the public in terms of collecting, annotating training data. So we dumped all of the imagery from Curiosity and set up a handful of train classes in a training document. and just put this online. And it turns out that you can easily train high school students or whoever else to annotate these classes. There was only about 6 of them. And we collected about 600,000 labeled images this way, which is way more than we ever could have curated internally. So, while this is very commonplace now, there's not a lot of training data on Mars that's available on the internet. So all of these big benchmark data that you train big foundation models with today that are just mined off the internet, like we can't do that. We have to find labelers for these things, and we have to train labelers for these things because it's such a unique environment. So this turns out to really work well in this case, and it's great outreach because schools and whatever I think have a lot of interest in doing this. So that's great, and we'll continue to do that in the future for you know future data annotation projects. All right, so how does this help us? So we talked about classical path planning, where we have a first stage heuristic, second stage validation. How do we infuse machine learning to make this better? And and the answer is kind of obvious here. So the problem is that that machine learning system is probably not validated, or it's probably not validated in that we don't want to fully trust it. As we know, deep networks make inexplicable failures that are very difficult to guarantee that they won't happen. But they're great for heuristics. So we want to basically replace the stage one um, cost estimate with a machine learning cost estimate that actually includes a collision estimation in its estimator. So instead of just a heuristic, it's actually trying to approximate what ACE is doing everywhere, and then you're having actual ACE validate the best paths that the machine learning algorithm found. So that's now the problem definition. So how we do this is basically the same problem for every location X and Y, every yaw, phi, and a height map M. We want to directly determine whether or not there's a collision or not at that position and orientation. So this is a classical binary classification problem, but you have a 4D input. But this works out really well with spatial models, given that um, you can estimate X and Y for all locations using, in this case, a fully convolutional network. And you can estimate it for a handful of discretized yaw angles. In this case, we just selected 4 different yaw angles as basically a stack of 4 spatial outputs. And you can train this basically in one shot. So this is a single feed forward, fully convolutional network with a binary classifier kind of sigmoid activation function in the end. Um, so this actually is really efficient to train and to run. So how does it work? So this was trained on a bunch of ground truth from actual Mars data um, that where we computed ACE at every location and orientation and just trained the algorithm. And this turns out to work pretty well. So we have about a 95% or so test accuracy. And again, it doesn't need to be perfect. Like ideally, we want to minimize the amount of kind of false negatives in terms of thinking something is safe when it's not. Thinking something that's unsafe when it's safe is actually fine in that you're just making yourself a little bit less efficient. But everything gets validated with ACE anyway, so this is like guaranteed to be safe overall. So in terms of its actual performance, really in every measure, this surpasses classical ENAV because obviously it's going to find better candidate paths than the simple heuristic. So in terms of the actual paths that it selects, they tend to have better path efficiency in that it's able to get to the goal quicker without making these kind of myopic or uh, you know issues with poor heuristics in terms of bad paths. Uh, it also surprisingly requires less computation because those paths end up being quite a bit better. You're having to evaluate kind of the overall path evaluation less. And so even though you're running this network across all possible paths, like your overall compute budget can be lower. So While this hasn't been deployed on the rover yet, we find this to be very promising and requires certainly more kind of V&V similar to how we validated ENAV, and that's probably going to be much more intensive. But for future Mars rovers, where we have the compute budget to run this, this is very likely to be kind of part of the solution moving forward. So I wanted to talk a little bit about a project that's ongoing now, where everything we've talked about to this point has just been approximation. So this is using ACE that's just estimating kind of a worst case bound. And oftentimes it can be kind of so conservative that you're not able to find valid or viable paths where they exist because you're just being so conservative. So what we wanted to explore is can we actually what is involved in actually computing true kinematic settling of the robot so we understand kind of true collision hazards such that we can drive a little bit less conservatively. So going back to the problem formulation of kinematic settling, um, is basically needing to estimate all of the joint locations of the suspension geometry and the roll pitch yaw angle of the body such that all six wheels contact the ground. So like as we talked about before, this is a nonlinear problem or nonlinear optimization problem. So you can feed this as a constrained optimization problem into a library like Series, which is a nonlinear solver, to be able to estimate a solution. And so while this is way too computational to run on the RAD-Z50 that is on Perseverance, it's actually not that computational. So this runs in milliseconds on like a modern kind of smartphone Snapdragon style compute platform. So for future missions, that might be viable. It runs at about the same time as ACE does, but has all of the same problems in terms of needing to run that all across all possible paths. That's still infeasible. Um, so what we'd like to do is take this actual kinematic settling solution and think about how we apply that to much further driving plans. So with Perseverance, it has a 6-meter planning horizon for the local planner. So what we'd like to do is take these actual kinematic settling solutions and apply them across what we're calling here a medium range path planner, which is going out tens of meters. So say like 50 meters of range, we want to compute a viable path using actual terrain data. Because we do have sensing that goes out that far. We have stereo that can give us range at 50 meters. The problem is that um, you have like any type of occlusion or occlusion boundary from things like rocks or relief, they cast shadows behind them. So you can't see behind them. If you have a hill that falls away, like you won't be able to see behind the hill. So like you're going to have holes in your map that degrade not just because of occlusion geometry, but also degrade because you're just losing resolution. Um, so you end up having partial data, and this is the reason, or one of the major reasons why we only had a 6-meter planning horizon is because you can densely populate that surface map at 6 meters reliably, even if you have some kind of missing coverage in your stereo. But if you try to do that 50 meters out, you're going to have huge holes in your map. And that is just very difficult to plan around. So the challenge here is we want to take actual kinematic setting solutions, which we're calling OBKS, that's optimization-based kinematic settling, across a digital elevation map that goes out 50 meters, which is going to have a huge number of holes in it. And we want to estimate not just what the traversability is in terms of the kinematic settling solutions at every location, but also for locations that we can't see that are inside the holes, can we predict what we expect it to be there? So it's using a very similar architecture, except now we have this occlusion mask, but basically that just indicates like what's missing in the occluded DEM. Um, Still a fairly conventional, fully convolutional network like a UNet, except it's using a conditional convolution on the input that's taking the occlusion mask in as its conditional input. And so the output is basically an infilled DEM that's estimating where all the missing data is, as well as the traversability. So these red locations is basically collision or not collision based on this optimization-based kinematic settling solution and the ground truth on the bottom, and then an estimation on the top. And this is tuned again to minimize false negatives. So it ends up being conservative, but it's now estimating true kinematic settling across very long ranges that provide good heuristics for very long path plans. So as we start to think about more high performance driving, as we start driving faster, longer distances, um, this will be a very important tool for being able to come up with path planning that's not so myopic and is able to maneuver around complex terrain that really requires far range reasoning. Okay, I'm going to try and zoom through most of the rest of this. I think I'm running a little bit short on time. Um, so in terms of science, we talked to a bunch of the mission scientists, which are like Mars geologists that are actually taking the data from Curiosity and Perseverance and trying to understand Mars geology and kind of the fundamental physical science element of it. And what we found out is um, other than the direct objectives of the mission in terms of like sampling very specific sites and doing very deliberative actions in terms of trying to um, to evaluate and inspect very specific locations. There's a lot of science that we just call in situ. As we drive by something, we oftentimes see something that we didn't expect to see it. We just happen to drive by it. We happen to image it because the navigation cameras caught it because they're doing mapping not for science but just for traversability. And a lot of the science actually comes out of that. So, for example, these little nodules, which are like calcifications that occur in the regolith, those became like a very of great interest to the geologists because they're an indication of water formation. And so, we went to these scientists and say, okay, like, how do you process the data? And they basically said that they go to their grad student and they say, go through like tens of thousands of images and like find all of the nodules and then map them out for where they occurred. And then, so they start trying to build these geologic maps by just going through this rote effort of digging through a pile of data to be able to make sense of it. So, this inspired a bunch of thinking in terms of like, how can we do better than that and apply some learning to make this easier? Because, in many ways, one of my colleagues actually drew this cartoon on the left. If something phenomenal were to happen, like some green monster were to walk by the robot, um, we might not ever know because the robot was never commanded to take a picture there. If it sees something it's never seen before, there's no reasoning about that on the robot. So we might just drive by something, absolutely phenomenal and never be the wiser because like, we don't really have any way to optimize what our data acquisition policies are to maximize anything. It's all deliberative. It's all, basically pre-planned. And so, how do we kind of think about both of these problems? So what we kind of envisioned is, as the rover traverses along, we systematically capture data, and we do this for multiple reasons, not just engineering, but there's a science reason for doing this, where every 100 meters or so, we just collect a random image of wherever it's pointing, and we uplink that. But the problem is, especially now, that the amount of data that we're able to collect in situ far exceeds our ability to actually transmit that data. Um, so, if we just collect video off of all of the cameras on the rover, that would probably exceed the bandwidth of actually downlinking those back to Earth by probably 2 orders of magnitude. So we don't do that, and we end up throwing away a lot of data just because there's no way to actually fetch it. There's like due to the kind of the satellite relay network, there's only so much bandwidth. And so, the thought is, okay, like if we're just systematically collecting, kind of up to the maximum of our bandwidth, an image every once in a while, why can't we just prioritize this? Why can't we, try and similar to with path planning, come up with a heuristic that tries to maximize what's interesting is from a science perspective about those images and put those in the front of the queue such that um, your actual science data might be a little bit enriched in the data that you actually downlink. So how do we test this? It sounds like a good idea. So and this work is actually a little bit old now. This I think in today's era where everything is transformer foundation models in large language models. This is obvious that you would apply a large language model or a vision language model to this. Um, this work is probably 7 years old now. So at the time, I think this was actually very controversial of trying to incorporate language models into vision-based systems. But basically, we incorporated a crowdsourced annotation system where we had a bunch of actually geologists or Mars geologist grad students to annotate a bunch of images. Um, and we learned a vision language model off of it. And at the time, this was using um, a model that was based on a architecture called hide and seek, if anyone is old enough to remember that, that used this kind of blue 4 score as an optimization metric. And this work actually worked out pretty well, actually. So, like in terms of kind of the bigram alignment of the predicted text, it aligned like well into 90% of the ground truth for a lot of these images. And so it allowed us to basically embed in principle, this isn't deployed on any rover, this is research, but principle allowed us to encode science queries on board, a hypothetical rover that incorporates kind of what is the science thinking of what the geologists are looking for, just as natural language. And then it would prioritize the imagery such that it kind of maximized the likelihood, at least according to the model, of the data being returned being well aligned with those queries. Um, and that kind of got us thinking around like how can this change our thinking for future missions? Because in many ways, like, we think about this as like Google search. Like we're trying to dig through our data by just kind of searching for it. So if all that data were available, we can just run these queries and get results. The problem is that, like I was saying before, like the ability to collect data far exceeds our ability to transmit the data. So, currently we have to collect the data off the instruments, downlink it from Mars to Earth. And this gets harder and harder as you go further out. And then we can search it. But why don't you just leave it on the robot? We have fairly tremendous capability for data storage now, and even in flight qualified systems that are radiation hardened, we can just store it and just have essentially a data center driving around on Mars, and we can query it from there. We don't need to downlink it. Just put the intelligence on the rover. Um, and this I think is really starting to be central to a lot of strategies. You think about like a lot of the AI companies now trying to put data centers in space. I mean, part of that is just due to power, but part of that as well is just putting the data where the connectivity is maximized. So I think there hasn't been a lot of work on this in the space world, but I do think that this is going to steer kind of the thinking in the future. Okay, in the last few minutes I have, I wanted to talk a little bit about when things go wrong. So I was saying before, like we've gotten nearly every rover hopelessly stuck in sand at one point or another. Um, we've had, like, if you remember InSight, which was deployed a seismometer to measure earthquakes on Mars, it had this mole, which is basically a drill that failed fairly spectacularly. Curiosity, its wheels on the bottom left. We didn't expect that the embedded rocks in the regolith would be so uncompliant. So it started punching holes in our wheels to the point where we were actually concerned that the wheels would start to shear off. Um, and they're like barely holding together now, where we have to drive the rover very carefully to avoid further damage. The very first sample that Perseverance tried to drill just crumbled. Like the material didn't match at all what we thought that it would be. And in many ways, like the drill was not an appropriate tool for that particular material. Um, and in many ways, like you expect the unexpected because we've never been there before. The best we can do is model with the data we have. This is always going to happen. And so how do we adapt? So I want to talk a little bit about stereo vision and how we think about adaptation. So going to this opposition effect phenomenon. Um, so if you look at the top right image of this is Buzz Aldrin's shadow, I believe, on Apollo 11. You can see that there's a surge of intensity kind of around his helmet, like where the camera is. Um, and that phenomenon is called opposition effect, and it occurs when the phase angle, which is the angle of the illumination from the sun, is aligned with the phase angle, the angle of the camera, the bore sight of the camera. So basically, when the sun is directly behind you, you see this phenomenon where you have this significant brightening as well as a significant loss in texture, because in these regions, the illumination is no longer dependent on the geometry. It essentially becomes constant. So you like in this kind of region, this halo kind of above the helmet, there's no texture, even though there's material there. There's rocks and everything else. There's surface geometry, but you can't actually perceive it. You can see this from orbital imagery as well. See this on Mars here, kind of aligned with the camera. Um, so this phenomenon is actually pretty prominent on Mars and on the Moon, and it creates issues with like stereo coverage here. So this is the from the stereo cameras on Perseverance. Anything that's colored is returning a disparity, a depth. Anything that's missing is where uh, it was not able to correlate. The stereo correlator failed. So you just get nothing. It's unknown space, which is fine. It's not unsafe, but if everything is unknown, then your rover gets stuck because you can't drive. You cannot drive into unknown space by policy. So we went off on an endeavor to try and understand, A, what is the problem, but B, like how do we potentially build a system that not just addresses it in terms of building something that can generalize better to more diverse domains, but how do we adapt to it? Like given a system that we say we didn't expect this to happen, how do we deploy a system that can observe it in deployment and adapt to it in situ? So we went back to Perseverance and looked at its entire mission to date, collected all of the navigation data that is available. So basically every meter of driving, we basically have a pair of stereo images from the navigation cameras. And it went through a bunch of diverse terrains. Every color here is a different type of geology, where some is very flat and simple, some of it's very rocky, some of it has a lot of obstacles. And we wanted to explore a bunch of different learning algorithms just to see like what can generalize better. The current block match stereo algorithm is very, I would say, classical, but also has very like simple or very kind of myopic failure modes because it's just taking a like a 7 by 7 window and doing a sum of square difference correlation across them to find a match between the left and right image. So we explored a handful of learning-based methods to be able to understand this problem. The first is what's called MadNet, and so this is a fairly simple deep stereo algorithm. And what makes MadNet interesting is that instead of trying to maximize for stereo disparity, where you're just trying to minimize your error against disparity ground truth, it's trying to minimize photometric error. So it's basically estimating disparity, using that disparity to warp the right image to the left, and then looking at the intensity differences between the left and the warped right image, and minimizing the photometric error between the two. So that's really interesting because you don't need ground truth. You have it only needs the intensity images of the left and right. Um, and you can use an actual disparity estimate from like a candidate algorithm as like a proxy ground truth to just accelerate the learning of this. But this is of particular interest because not only is it learning based, but it's self-supervised. It's like so it can learn in situ kind of without knowing the ground truth of where you're driving. Um, so the other two methods that well we explored a bunch of methods, but the other two that I think are notable that are kind of in the realm of state of art methods today. So the next is Raft, and Raft is interesting to us because um, unlike MadNet and a lot of these so-called cost volume methods, Raft has an iterative element where it has like a gated recurrent unit that continually refines a disparity estimator, which overcomes this disparity limit because with the cost volume estimator, you have to have a fixed 3D volume where disparity is one of those dimensions, and it explodes in complexity really quickly if your disparity search goes too large. So it ends up being a fundamental limiter. But with this method, since it's iterative, you're not limited by that. And furthermore, because it's iterative, it's like an anytime algorithm. You can run it for additional iterations to get additional performance. And lastly is what's called IGEV++. Um, and this method is very similar to Rath in that it's also iterative, but it encodes kind of spatial context. So this is like the most complex of the three models. It has all of these encoders to try and understand kind of what the spatial features are around the correlation locations, to be able to, essentially have kind of spatial, like object-based priors around what you would expect around certain geometries. It's also iterative. It also doesn't have limitations around max disparity. So those are the three methods that we wanted to evaluate for potential deployment on board a candidate flight system. And for comparison, we wanted to know kind of what was the extreme of learning-based methods. So we wanted to compare all of those with foundation stereo, which I think is still the state-of-art model today. It's a foundation model. It uses, it's kind of a kitchen sink of every state-of-art kind of component in deep learning today. So it has depth-based priors using depth anything v2. It's using kind of foundation model image descriptors. It has a lot of iterative refinement kind of based on all of the previous methods. So this model is enormous. I believe it's over 1 billion parameters. And it requires very large GPUs to run. It's not practical for online deployment at all, but it produces like nearly perfect results. It's actually like people are calling stereo kind of a solved problem due to methods like this because they perform so well against benchmarks. The problem is that they're so big that they're not really viable for deployment anywhere. But we wanted to compare like what is the given technology today, what is like the ultimate limit of what we potentially could achieve and how do these methods compare to it? And because we don't have actual ground truth on Mars, it would be great to have a LiDAR or something. We don't. So all we can do is compare it against what our flight stereo is doing, which is very carefully validated to produce accurate ranging. It produces bad coverage in that when the correlator is below a correlation threshold, we just don't return a result. But when it does return a result, those typically are very accurate. So that's kind of our pseudo measure of performance here, comparing these deep methods. And I know we're kind of pushed on time. I'll kind of jump straight to the conclusions. So this is a qualitative rendering of what these results look like. The terrain on Mars, like while complex for rovers, is not terribly complex compared to street scenes. All of these deep methods actually perform quite well, but with a lot of notable differences that I'll talk about in a second. So what I really wanted to focus attention to here is MadNet. So MadNet ORG is pre-trained MadNet that is just trained on the pre-trained models are all trained on the same data sets, which are benchmark data sets, mostly from Earth data, where you have millions of images of true ground truth stereo pairs. And MadNet Adapt is basically the pre-trained model that has been run to do online adaptation. Every time you see an image, it will adjust its weights online based on that photometric loss. And then foundation stereo, which is kind of the baseline for kind of what we're trying to compare everything against. So if you look at the comparison of performance against flight stereo from Perseverance across all of these methods, foundation stereo kind of by far is the most accurate. So bad 0.5 is like what percentage of returns are worse than a half a pixel of disparity difference from flight stereo. So for the non-adaptive methods, foundation stereo is by far the best. But what's interesting is that once we incorporate adaptation, MadNet actually exceeds it. And I'll kind of jump to this plot here where so on the left side here is performance as a function of complexity. So here is like the floating point operations required to run that model feed forward. And here's the error rate in terms of endpoint error, or this is actually like how many pixels are greater than one disparity of error. So for the best performance, sorry, I'm trying to find yeah, okay. So the best performance, kind of ignoring this block here, is foundation stereo, but the amount of complexity is enormous, right, compared to everything else. If you look at MadNet, which is the simplest model out of all of the ones that we evaluated pre-trained, it performs by far the worst at very low complexity. But with just like one epoch of adaptation, this is actually outperforming kind of the best state-of-art model on Mars using like two or three orders of magnitude complexity less compute. So that's kind of the punchline here is, we keep thinking about these big foundation models as trying to generalize to everything, and that's great. But the problem is that you have to pay enormous cost for that. And at least in this case, what we've seen is taking a very simple model that generalizes sensibly, not great, but sensibly, and just allowing it to see some data in the deployed environment, and you can actually perform better by incorporating generalization plus adaptation over just looking at generalization using these like enormous foundation models. Um, so I want to talk a little bit about kind of similar applications that we've used for this idea of adaptation across a handful of projects that we've done in the past. So this is a couple years old where we had a husky like trying to drive through vegetative terrain. And this is really hard because like sensing vegetation geometrically is just really hard. It's like you got a lot of small stems. We had a LiDAR. You just get returns everywhere. It's very hard to map vegetation and be able to understand like what the density of that vegetation is. Can you drive through it or not? You can just avoid it if you want. But in this case, there's some vegetation like grass that you can just drive right through it. But there's some like heavy brush where if you drive through it, like you'll just get stuck. You can't push through it. Um, so we have these proprioceptive sensors. We put some load cells on the vehicle, and which measures kind of the interaction forces with material, and just started driving it around and collecting data, and kind of threw this into a volumetric model. So this is a little dated now, but it's using VoxNet to be able to correlate the LiDAR returns of what it sees with the load cell data of what it feels, and basically providing a prediction of using a Terra mechanics model to understand kind of what the interaction forces are for that material, such that you can then plan around, driving through material that you know is traversable. So you can see like heavy grass and say, okay, I can push through that, and the planner will learn, or the perception system will learn that it's able to drive through that material, whereas like heavier brush and whatever, it will avoid. And so even though geometrically they all look the same, um, it can learn to start to differentiate them based on subtle details of how the LiDAR returns between these different materials to be able to differentiate what it can actually drive through. In a very similar vein, this is actually much recent work. This is just from in the last year. We've been working a lot with quadruped robots, and these are really interesting because as a platform, like they're very robust. Like you can test a lot of material that are untraversable, but you can kind of try and do some foot placement on that material and assess whether or not it's stable. And if you fall over, like typically you don't break the robot can get back up, but you learn something from that. And so here we have, basically a fully adaptive perception system that is learning by example. So it's understanding if it can walk safely on the surface it's walking on, then it's classifying that as safe. And if it crashes on something, or if it feels that it's an unstable foothold, it will label that as unsafe. And so that's the bottom right here is basically the result of that map. And it's learned completely self-supervised. And this is using actually much more sophisticated models. So here we weren't worrying about compute. This is using a foundation model. I think it's like a Dyno V2 style feature descriptor. And what it's learning is an adaptive reprojection of those features, based on proprioceptive. So this is running on a big workstation that, we don't care about compute here. We just wanted to know like what was possible. Very similarly, when talking about stereo is a very computational algorithm, especially if you do it at high resolution. And it's really hard to run stereo on these like flat terrains with lots of reflections. Like this is a really difficult use case for stereo. So the question is like, do you even need stereo? Like we have a lot of very interesting work with depth from a single image, but the problem is that it's unscaled. Like you don't actually, it's not calibrated to produce metric depth. It's like normalized depth. And so the challenge is like, how do you actually normalize it? And that has to be done kind of in real time. So the idea was, okay, we have a LiDAR that's very sparse. So you can't produce an accurate high density map with LiDAR, at least in this case. But we have a single camera and we have this depth from a single image method. So how do we refine this such that we can continually update the weights of that depth network based on the LiDAR data to be able to produce more accurate depth maps that are geometrically consistent with the LiDAR. Um, so yeah, I think that's all the material I had. Sorry, I ran a little bit over. Thank you very much for humoring my talk. Any questions?
Hi, Brandon. Can I start with the questions? So first of all, thanks for your great talk about the space robots. It was very interesting. Then I have actually just a quick question about the collecting training data through the crowdsourcing.
Mhm.
Yeah, since the soil on the other planet like the Mars and can be different from the soil on Earth. So I was a bit surprised that you asked the high school students to label images through the crowdsourcing. So I'm just wondering because it sounds a little bit risky. So how do you check or confirm that their labels are correct? Do you have any verification step or something like that?
Yeah, there's a lot of science on this actually. So like back in the mechanical, like the Amazon Mechanical Turk days, they would pay like random people like one US cent to annotate an image, and you just get garbage because people they just want to get money, and so they just they do garbage work. And some people do good work, but you have this mixed bag of really high quality results and just terrible, terrible results. And even worse, you have like adversarial results where they do the exact opposite of what you want to do just because they hate you. Um, and so you have to figure out how to tease all that out. So there's kind of there's established mechanisms for being able to it's like a market process where you have certain examples that are annotated by multiple people. You look at concordance. You also
Ah,
have a weighting system where you start to upweight or downweight annotators so
mm,
that they either get easier or harder examples, or you start to discard their examples if their quality drops. And of course, you have some kind of manual review by an expert afterwards to be able to make sure that system is working. But yeah, we didn't invent any of that. I think that a lot of these crowdsourcing platforms have that cooked into it. And they thought about all of those problems and they work pretty well.
okay, I see. I got it. Thanks.
All right, so from the perspective of autonomy, what's the biggest bottleneck preventing planetary robotics from behaving more like adaptive learning systems rather than pre-programmed ones? Um, well, I think that I wouldn't say it's a bottleneck per se. I think adaptive systems are very difficult to validate. Like when we think about how we test a system for correctness in the formal sense, but in the less formal sense is just how do we perform enough testing that we're convinced that it's going to operate in the deployed environment at the same performance level that we see with local testing. It's really difficult to do that for an adaptive system where that system is designed to adapt to an environment that we've never seen. So simulation, I think, is a huge piece of that today. Especially there's a lot of work now on this kind of whole sim to real gap and world models and all of the work in those domains to try and while you may not know exactly like what domain you're going to have to adapt to, you can at least look at the adaptation problem across some perturbation of sensible domain shifts to just understand kind of what your adaptation properties are, but that's a whole level of new testing that like we never had to think about before. So I say the challenge is like how do we deal with that in a way that we're comfortable with the risk? And in many ways, like there's a lot of unsolved problems there. So that's still research. So I think NASA will get data from robots on Mars. What communication do you use and how much delay is there? Um, so the communication mechanisms are there's several Mars relay orbiters. So two of them NASA operates. It's the Mars Reconnaissance Orbiter and Mars Global Surveyor. Um, there's, I believe, three other orbiters that belong to other nations that have collaborated with NASA to provide relay services. So every time there's a flyby of that orbiter, you can relay to that spacecraft. And then that comes to what we call the deep space network. So we have three 70-meter antennas that are like one's in California, one's in Australia, one's in Spain. So 120 degrees apart. So we can see every point in space at any given time. So the DSN has to be pointed at that orbiter to be able to get communication. So two things have to happen. You have to have an orbiter fly by, and DSN has to be pointed at the orbiter to be able to get data from Mars to here at high rate. If there's line of sight, if the rover on Mars happens to be facing Earth, there is a direct-to-Earth communications through onboard antennas on at least Perseverance and Curiosity, but it's a very low-rate antenna. Direct-to-Earth communications is typically just for telemetry. You just send a couple bits. As far as like image data, it has to go through the Deep Space Network.
Okay, okay, thank you. Is there any question in the front?
I have one more actually, but that is a very quick question. So, Brandon, do you still have the projects on the robot grasping?
I'm sorry, projects on what?
Do you still have a project about the grasping some objects on the using the robot? I mean, when I was there as an intern, then our project is about the grasping, right?
Yeah, yeah.
Yeah,
Less so on
yeah.
Mars. I mean, there's no like grasper on Mars. Like we have a drill on an arm.
I see.
So for Mars, no.
Must
But
know.
I think most of the manipulation work of interest is two places. There's in-space assembly. So I think building large structures in space end up largely requiring manipulators. So that's like a very hot topic now, and especially with the kind of the movement to start to go back to the moon, and especially with trying to build infrastructure there to support human astronauts going back to the moon. Something has to build that infrastructure. So I think there's a lot of interest in like how do you send up robots there that are generic that can actually build things, manipulate things, construct things. And manipulation is going to be a major challenge there. But I think both of those worlds are still a lot of work to be done. As you know, manipulation is really, really hard to do robustly.
Yeah, right. But I just, how can I say? So then I just think about that manipulating some objects on the other planet is actually that can be very challenging because of that objects can be very different from the object that we can observe on the Earth. So I don't know how we can handle them. Yeah.
Yeah. Yeah, I mean, in principle, it would be great just to like, send a generic spacecraft with manipulators and drills and every tool that you need to do any job that you can think of. It's it's not the way that we typically design missions, right? We design missions now like that have very specific instruments for very specific. Like we don't send a Swiss Army knife to different planets with everything that with everything you might need to solve an unknown problem. But I think in the future, like we'll have to because we don't to be able to deal with this kind of adaptation challenge. You're going to have to send modalities that are generic and robust enough to be able to accommodate kind of a wide variety of manipulation and mobility tasks.
Okay, great. Thanks. Then it seems that you have two more questions on the chat.
I see it. So a simple question about the power issue. Computational resource demand will be high for things like manipulators, camera sensors, wheels, processors. Want to ask, how does NASA solve this problem? Well, so power storage, I mean, it depends on the application. So for Curiosity and Perseverance, they have a nuclear power source. So it's using what's called an RTG. It's a radioisotope thermal generator. So basically, it's a plutonium pellet that you have a large thermoelectric heat dissipator that you generate electrical power from the thermal gradient of plutonium decay. And while that works great and for a very long time, I mean, it has a half-life, so like the output of that battery decreases over time. But it generates it's like several hundred watts of power, which is not a ton. It's like a light bulb. But it's enough to heat the rover and drive the motors and run a very simple computer. And that's like the day that ships is the most power it will ever produce, right? So it's an exponential decay. So they're designed to last about a decade. So I mean that's how we typically will power anything that can't viably get solar power. Solar is definitely better in terms of like most orbiters are solar for obvious reasons. most spacecraft that, you know, at least near Earth tend to be solar because you have enough solar flux to generate sensible power. You know, it's about a you know, kilowatt per square meter. So, you know, beyond like that's the kind of power that you're dealing with is, you know, a kind of a kilowatt at the maximum, you know, which, you know, I think if you have a RTX 4090 GPU in your workstation under your desk, that's probably drawing a kilowatt like on its own. And it's doing nothing else like driving around. So, you know, it's a challenge. Like once you start thinking about, you know, not just powering the electronics, but thermals, you know, like a lot of these spacecraft are flying or operating in an environment that's, you know, potentially, you know, negative 200 Celsius, and equipment doesn't work at that temperature. You have to heat it. So a lot of your power goes to heating. So your power budget, you know, it's not just the computer. There's a lot of stuff that takes power that you kind of wouldn't expect for spacecraft. There's not a great solution to that. You know, I think like once they start to miniaturize, you know, fusion reactors and all that, you know, decades down the road, maybe that'll be an option. But, you know, right now, thermal and RTGs are really the only viable power source for most spacecraft. See, in your opinion, what do you think is the most important competency for NASA? Wow, that's a loaded question. You know, I think there's a lot going on at NASA, you know, so I think like for everyone here that's working in machine learning, AI, robotics, like all of that is super relevant. You know, if you're interested in joining us, you know, please, you certainly like reach out to me or, you know, go to, you know, online. They have, you know, ways to submit your interest. And, you know, as you know, with the current kind of political landscape, it's been a little bit challenging, you know, at most of the federal agencies, but that's not always going to be the case. So if you're interested in space, like, please talk to us. We're always looking for talented people in robotics and engineering.
Yeah, so for instance, do you still receive the international students as a research intern? Then, but actually, some of my students are very interested into applying the research intern.
Yes, we're always interested. So yeah, please, like I said, please reach out. You know, sometimes there's not a great fit depending on what projects are going on. Like as you know, with internships,
Yeah.
at least in robotics. So like
Yeah.
for JPL, like even though it's known for robots, like the robotics section is actually very small.
Yeah, I know.
We have a handful of projects, and there's good alignment between the projects and, you know, what you're working on. You know, there's always opportunity, I think, for funding interns. So, you know, again, like if you're interested in some of the work that we do, you know, please just reach out. Like find a project, find the PI of that project, and just reach out. And you know, if there's a good fit, then, you know, that's great. Like we're always interested.
Okay, great. It's a great news. Then I will talk to my students about who are interested in the applying the internship to the NASA.
That's great.
Okay, thank you. Thanks so much for your great talk again. Then stay in touch. Yeah.
Yep. Thank you for the invite.